Alright, good afternoon. So let's start our course today. We are going to talk about the chapter 3 of our textbook. The topic is image processing. And since this is a course of computer vision, why do we need to care about the image processing? The reason is our input of computer vision is image. So we need to try to use any possible method to get good input. It means the image. Okay. So there are many kind of image processing methods, and the easiest way, I should say the simplest one, should be the pixel transform or trigger transforms. It means we adjust the pixel's value by itself. So let's take a look at those 6 images. So the A means, suppose this is a given input, and if I adjust its brightness by suppose, okay, the intensity of an image is integer from 0 to 255. Okay. And if we adjust the brightness by adding 16, then we will get this image. It is slightly brighter than the input image A. And also, we can multiply the factor, say 1.1. Then we will also get another image like a C. So what the difference is, if you see the histogram of the 2 images, they are the same in B, only with a shift. But if you see it in, so see the shape here and here, they are the same. Okay, this is only a shift. But if you times a factor greater than 1, then you will extend the histogram. So you can see the histogram here, it is slightly stressed. Okay. And there is if you apply a gamma function, I will show gamma function in the next slides. And this is for histogram equalization. So you see most of the intensities are the histogram of the temperature is like a horizontal line. Okay, and this is the partially histogram equalization. And let's see what is. So let's first discuss what gamma is. So this is a very old TV. It's called a CRT TV, and the CRT stands for cathode ray tube. It's this part. Okay, so because it's a physical property, when we give an input voltage, then the brightness of the generated brightness is not a linear function of the input voltage. So it looks like an exponential function, and the power order is around 2.2. Therefore, if we want to get the brightness as we expect, then we need to adjust the input function with a inverse curve. So this is the y to the order 1 divided by gamma. Okay, so this is called gamma function. So what can gamma function do? Let's look. So if suppose we have the input image like this one, then when we apply a gamma function, the generated image give me certain kind of contract, and some people prefer or like this contract. So for different companies, they set different gamma values in their monitor. Okay, so for Mac, the Mac OS use 2.2, right? And let's talk histogram equalization. Okay, say this is the input image, like A, we see, and we can accumulate the intensity of each pixel and draw the histogramization chart here. Okay, so there are 4 different components: green, red, blue, and white means brightness or illuminant. And we can draw the accumulated curve like this one. So see the D, we can use the chart C to create a mapping functions. The only difference of chart C and D is the Y histogram. So you can see here. Here is from 0 to around 3,500,000. And here we change it from 0 to 255. So D become a mapping function. Given a point in the input image, we use the mapping function to generate its new pixel values. So here you can see it become quite bright, and its histogram shown in this chart are equalized region by region. So this is called histogram equalization. And in this slide, we saw the partial equalization here. Okay. The partial equalization means we have a vector alpha. We use certain, I should say, suppose I is the input original image, and the CI is the histogram equalized image. Then we use partial original image and the partial equalized image to generate the new image. So this is called partial histogram equalization. Right? Okay, then we show some color spaces. So most of it, I should say, given an image, okay, suppose this data is from, for every pixel, there are 3 channels, yellow, green, and blue. This is the most color space you used. Okay, and you see if the value is greater, then there is more, it is redder, greener, or bluer. So this is the RGB color space, the most common one we used. And if we separate its 3 components, we will get the R channel, G channel, and the B channel. Okay, for this flower, because the color is purple, so the blue channel is quite the. You see many bright values in the blue channel. Okay, and in the contrast for the background is almost green. So you can see there are many high pixels in the green channel. Then you can convert the RGB channel into the small lowercase r, lowercase g, and lowercase b channel. It means the ratio of the 3 channels, right? And there also is a L star, A star, B star, and the hue saturation value. Okay, let's take a look at what they are. Okay, first the hue saturation value, HSV color space. This is an intuitive color space. For most people, when we see a color, we have the sense. Okay, this is brighter or darker. If they are red, yellow, green, blue, purple, it looks like a circle. Okay, so this is the hue. The meaning of the hue is, and also there's pale the color or very saturated color. So this is axis saturation. So we try to describe a color use the hue saturation value. Then okay, we get a very straightforward intuitive description. Okay, so what is the relationship between those colors? However, in addition to the HSV color space, there is another color space called HSL. For hue and saturation, the concept is the same. The difference is in the HSV value, it always assumes the most saturated color occur when the brightness is high. So you can see this is the most saturated color, and its value is the highest one. But is it true? Okay, well, say this is just an assumption. Okay. So for the HSV value, it has a different assumption. It assumes for the most saturated color, it occurred in the middle range of the lightness. Okay, it means for very bright color, you cannot distinguish its saturation and hue because all of them become white, very bright. And then for very dark pixels, you also cannot distinguish its color, its hue and saturation. But in HSV, there is only a single way. Okay, it assumes when the color is very dark, you cannot tell the difference. But when the color is very bright, you can clearly distinguish them. So which make more sense. I personally think HSL makes more sense personally. Okay, but HSV is a widely used, very long-standing color space. Okay, so given an example, suppose this is the input image, then we convert it to the hue, saturation, and value space. So value is almost like the brightness. You can see it's just like a grayscale image. And the hue, so see the sky is blue. And so for this region, you can see the hue is a certain value, okay? And however, when you see the shadow area, you also see it is almost the same as the sky region. The reason is when they convert to the HSV space, color space, their hue value are the same. But how for us, okay, it is difficult to sense. So there is another color space called CIE L star, A star, B star state. It's the perceptually uniform color space. It means for every 2 points in the color space, if their distance are similar, okay, then we should feel they are very similar colors. Okay, so this is the same input image, and when we convert to LAB, L is also the brightness or the lightness. And the difference is how to describe the channel A and channel B. So how to calculate the CIE LAB? In our textbook, you can find this page. So from equation 2.106, 2.108, then this is the equations to calculate the CIE/LAB color space. So basically, the psychologists try to find a way to measure those colors and try to make them similar. So it is calculable, but I want to skip the details here. I just want to deliver a message to you. This is CIE colors, LAB color space used to measure the difference of colors, and they can use the same metric for all colors. So let's go back to our biology principle. Why can we sense color? Because in our eyes, there is a very thin film called retina. Okay, and on the retina, there are 4 kinds of cells. There are cone cell and rod cell, and they play for different roles. Cone cell is to sense the brightness. It is cone cell is sensitive to different wavelengths. So there are 3 different kinds of. It's a long cone, short cone, and the medium cone. So, and the rod cell is sensitive to. It is not sensitive to it is insensitive to color, but sensitive to brightness. So when we're in a very dark room, our cone cells do not work. Only the rod cells work. So we cannot sense color in a very dark room, but we can still see the object. So the CIE color space, it means in 1931, almost 100 years ago, the CIE institute, they standardized the human sense for different color. Okay, they use 3 different pure wavelengths. Okay, they are, okay, let's see. The 3 different kind of light is 7 nanometer and 546 and 300. So this is blue, this is green, sorry, this is red, this is green, and this is blue. They use the 3 different pure light to on the side of a board, and they try to adjust the wavelength of on the another side of the board, and ask a human subject to adjust the intensity of the blue, green, and the red light through a very, very small hole. The degree of the hole is only 2. So this is a very, very narrow hole. Okay. So the object looks like this. So for this side, okay, it can adjust the 3 kind of light sources, the intensity. And for another side, it is fixed. Okay, it is controlled by the scientist. So the question, why do they use so small hole? The reason, okay, is that the row and the cone cells on our retina are non-uniformly distributed. At the foveal region, okay, this is a very small hole on our retina. There are a lot of very high dense cone cells. So you can see the distribution here. In this region, there are a lot of cone cells. And the cone cell is the cells sense color. So for us, only in a very, very small region, we can sense color well. And for other regions on our retina, we are more sensitive to brightness. Okay. But otherwise, you can try. I should say, you can stare at a certain fixed point on the wall and ask your, I should say, classmate, show a color somewhere here. Can you sense the color or not? Okay. So this is the histograph. Those cells on our retina. Okay. Therefore, they need to use a very, very small hole so that they can accurately measure the similarity between 2 different colors. Okay, when they standardize the stimuli of the 3 colors, they get this chart. So it means for any kind of color, it can be a combination of the 3 primary colors. Okay. But however, you see a negative value here. What does it mean? It means you cannot add the red color on this side. You only can add the red color on the other side, so the colors on the 2 sides can be balanced. So that's okay. Oh, let me show you another example. Say, okay, if you have a color, it is generated, it is around 600 nanometer here. Okay, it means you can combine red color and the green color to generate the color. It is generated by the wavelength of 600 nanometer. And you also can, okay, however, but if you want to generate a color of the wavelength of 480 nanometer, it means you will use green and blue on this side. Okay, green and blue on this side, but you need to move the light of the red primary color to here, to add to here. So suppose the green light is 408 nanometer. You need to move it to another side. So you get this negative values in this region. So, yes, any question?
So I was going to ask, so the red, green, and blue here represent lights that the researchers chose for the experiment. Which are those three ones just showing the other image?
Yes.
That's correct, right?
Yes.
Yeah,
okay. So, however, this is inconvenient. So we, okay, they create another color space called CRE-XYZ. So here you can see it is just a linearly transform from RGB to XYZ, and there are two advantages in this color space. First, the Y is almost the same as the brightness. It means the brightness. And the second is all XYZ values are positive. So we don't need to use negative values anymore. Okay. Then if we convert the XYZ, so we see here, okay, let's go back. We see here the lowercase r, lowercase g, and lowercase b just means the ratio of the three components, right? And here is the same. We use lowercase x, lowercase y, and lowercase z. It also means the ratio of the three components too. And if we we draw the small x and the small y on a plane, okay, then originally we need to use three components to describe a color. Now we can only two values to describe a color, regardless of, okay. Then when we draw this one, so this curve means the wavelength, the result of the wavelength from 400 to 700. Okay, and the 3 points here and here and here, okay, it is the three primary color. The three primary color is this one: 700, 438, and 561. So, okay. So if we want to, so for color in this region, okay, can we use positive values to combine the 3 points to get this region? No. Okay, so you need to set some negative values. That is the reason why here are some negative values here, because they are, if we say, because they are too gray to be a positive combination of the red. Red is here. This is red. Too gray to be to combine the red primary color. So it has to be negative. Okay, so this is called a color gamut. It means the region your device can show the color. And here you can see many small circles here. Okay, it means for this region, we feel their colors are almost the same in this region by region. So you can see they have different directions. Okay. And okay, now maybe you have ever seen this image before. It means for different companies, they have their preferred color gamut. Okay. So human. This is our human. Our human eyes can sense all colors in the color gamut. But for our devices, either you have for example, say a monitor, the limit of the color can be shown on the device will draw by the color. Or if you have a photo, real photo, okay, the color can be shown on the paper. It has its limit, and this limit can be represented by the gamma. Okay, so this is for monitor. So for Microsoft and HP, they selected the sRGB color space. So sRGB is this one, is the blue one, this one. This is quite small, okay? And for Adobe, they set their own RGB color space. And the NTSC, it is a television system. It has its own color space. And the CIE RGB, that is the one we use the 3 primary colors to describe. Okay, so what does it mean to you? Okay, let's see this. When you want to purchase a monitor, you often see this spec. It means the monitor can show 100% of the sRGB gamma color gamut. Okay, and also you see this is also this one. So for the high, it means it match your minimum requirement. It can show certain colors, but there are some high-end monitor. It may claim we can show 100% Adobe RGB. Then it means the quality of the monitor is much better than another one. Also, you will see another spec. It means delta E. It means how to calculate the delta E. It means if you convert those values in the LA, CIE LA star A star B star space, then because we say it is a uniform space, so you can calculate the difference of the two colors. It means so okay. If the delta E is very small, it means you cannot sense the difference. What difference? The difference of the data and the physical world. Okay. So now, given the color presentation, okay, we say when you have a file or when you have an image, it is represented in data, a lot of numbers, right? So when you show the image on a certain device and the certain device follow a certain spec, then you can clearly know the color in the physical world is associated with the data. Okay, so right. Okay, now we mentioned it earlier. Image processing, you can treat it as a helper for computer vision. And let me show you an example. How other researchers use image processing, or you just use the color space for their computer vision task. So this is a paper. You can see the paper is published in 6 years ago in the International Conference on Biomedical Robotics and Biomechatronics. All right, fine. So what they want to do is they want to use a robotic arm to help some patients. They cannot use their hand well. So the idea is they have to have a camera on those patients' wrist or hand, so like this one. And they can use a robotic arm to help the patients to get some object or grab some object. Either it is a wearable device or it is just a remotely controlled separate robot. Okay. So, for example, if they want to grab the iPhone, how do they do? First, they have an image and they know the background of the in this image. Then first they change the color of the iPhone. From if there is some gray pixels on the iPhone, it converts it to green. Why? Because they want to remove the shadow of the object. The shadow, there are often shadows on the background or in the background. Then they convert this image to the HSV, so say hue, saturation, and value color space. Okay, then because the color of the shadow usually is gray, so they can separate the green color and the gray color by what? By the hue and the saturation. For green color, no matter its brightness, the hue is always, the saturation is very, very small. Okay, so they separate them by the saturation. Then it can get the segmentation and do some binary operation, and they can find the weight of the object, and they can use their robot arm to grab the object. They need to find the orientation, so they need to find the easiest way to grab it. Right? Okay. Here, okay, let's show some. So we just say the pixel pixel adjustment. Then pixel adjustment is we adjust the pixel by the value itself. Here, the linear filtering means we adjust the value of the pixel by its neighbors. So the most okay. There are several different filtering. So let's show this one. Suppose we have input the image F, and we have a kernel, we usually call kernel or mask, like this one. Then we do a correlation operation or a convolution operation. They are equivalent. The only difference is if we do correlation operation here, we use the positive X and the positive L here. If we do convolution operation, we use the negative X and the negative L here. That's the only difference. So they are equivalent, just a different side. Right? Okay. And let me show you an example. This is the box filter. So box filter means every pixel has the same value. Okay, so every pixel is 1/9, right? And okay, suppose this is the input image F, and we want to compute the point here. So it means we multiply every pixel with the box filter, its corresponding weight value, and sum them up. So this is 0. This is also okay. Here we got the first value. It is 90 divided by 9, so it's 10. And here we got the summation is 180 divided by 10, so it's 20. And the set 30. Then go through every pixel on the image. Then we got this. Okay, so this is the input convolution operation and the output. And let's show you an example. Okay, so the left one is the input image, and this is the kernel, and this is the output image. So it can quite blur. And there are some property. Let me show. Okay, so this is the original image. If you have a kernel, there's only single value 1 at the center. Then you will generate the identical result. There's no difference. But however, if you shift the pixels from the center to its nearby neighbor, then you will get the result of the shift operation. Okay. If you combine, or I should say, if you combine two kernels or masks for this one and minus another one, then you will get the result of sharpening. So this is the output. The reason is, I should say, this is a high pass filter, and okay, it enhances the high frequency signals in the image. Then, so we see more high frequency details in the output image. So it looks like a sharpening result. And then there's another filter called Sobel filter. It looks like there are two different types of Sobel filter. This is a vertical one. Okay, input image filtered by Sobel filter, and so you can see because this is a positive number and this is a negative number, some output value will be negative. Do you agree with it? Okay, let's say here I should say okay, convolution or correlation. It means the weighted sum of the surrounding pixels. Okay, and here, since we have some negative values, so when you see, okay, for example, this region, okay, the left part is dark, okay, so the value is small, and the right part is bright, and the value is large, okay. If we use the correlation operation, it means some small value will multiply by the three values, and then some bright pixels will multiply with the negative values and sum them up. So will it be a negative value? Yes. Okay. So here, that's the reason why we take the absolute value, because how do you show a negative value on a monitor? No way. The monitor only can show positive values. Here we show the absolute value so that we can show either negative or positive values. What does it mean? So it means the response. If you disregard the negative signs, it shows the response. The brighter pixel in this image, it means the response of the Sobel filter respect to the input image is larger. So it means the vertical Sobel filter has a strong response for vertical edges. So see where is the vertical edges in this image. You can see here. It's a very strong vertical. So you can see the strong response in the filter image. The same for horizontal Sobel filter is, so where is the strong, or say significant vertical, horizontal edges in the input here, okay, and here, and here. So you can see the very strong response in this region. Alright, so if we want to find a gradient, then there is a gradient filters. This is a horizontal gradient filter, and this is a vertical gradient. So you can see, actually, the vertical gradient filters are very similar to the Sobel filters. And then let's show something. Let me show an image here right now, right here. So this is mean the separable linear filter, and you can see this is the gradient filter. Okay, and if we, so it means a Sobel filter can be separated into two different filters, one for horizontal and one for vertical. And for this, it is a gradient filter. And here is a bilinear filter. So a Sobel filter is a combination with a bilinear filter and a gradient filter. Okay, let's go back to our. Okay, so for linear filter, they have some properties for linearity and or called superposition principle. It means if you have two kernels, if you have two images, f1 and f2, if you combine them together and apply with a filter, then the result will be you apply the filter on the two images and combine it. Because every operation is linear, so it will happen. Okay. Another the set. So for the two equations, okay, they mean the same thing. But our textbook, you will see the expressions twice in 3.5 and 3.6. They are the same. They mean they are totally identical. Okay, but I don't know why our author write them in two different forms. All right. And then another property called shift invariance. It means if you shift the coordinates, then no, it's fine. And when you apply if there are two images, one is just a shift of another one. So F is an image and G is another image. They are just a shift. You just apply a shift operation to get another one. Then when you filter the G image, you will get the same result if you apply the filter on F and shift them. And here, okay, this is some example of the separable linear filters. A box, as we say it can be separated into a vertical and a horizontal one-dimensional filter. And for boxes, all of them are one. And for bilinear, okay, it is the same. And the Gaussian, okay, we will show Gaussians later. And here is the Sobel filter, and this is a corner filter, right? So why do we need to care about are they separable or not? The reason is, see, if we want to apply a linear filter to a two-dimensional space, a 2D space, then how many operation and summation we need to take? Okay, yeah, so here, because it means, say, there are k-square points here, right? Suppose the dimension of this is k, then because it's the square metric, so there are k-square pixels. Then, for a linear operation, we need to have k-square multiplication. This is a kernel to its input image, and then sum them up. So there will be k-square multiplication plus k-square addition. So then we can get the filtered pixel. However, if we can separate a two-dimensional kernel to single one-dimensional kernel, then our operation would be, we can apply the vertical kernel and then apply the horizontal kernel. Therefore, the totally computational cost will be reduced to 2k multiplication plus 2k addition. So this is the reason why we need to care about whether it is separable or not kernel. If it is, then we can compute the result very efficiently. Okay. All right, so let's talk a very important filter. It means Gaussian filter. Okay, so this is a mathematical expression of the Gaussian filter, and this is an important parameter called sigma square. Okay, if the sigma square is small, say this one, then the distribution is highly concentrated at the central region. So like this one. And the sigma square, the square, it is mean the variance. If the variance is large, then the distribution is shorter and widely distributed. Okay, so if we apply the Gaussian filter to our image, it will be like this. This is the input image, and if we apply a variance, a standard deviation, a very small standard deviation, say just 1 pixel, then you can. It's very difficult to spot the difference. But if we increase the standard deviation, then we will apply the Gaussian filter. We will get a blur and blurred images. And let's compare the Gaussian filter and the box filter. So this is the kernel of a Gaussian filter, and this is the kernel of a box filter. Then, do you see the difference? Oh, yes. Yes, correct. Yeah. So you can see there are some vertical and horizontal patterns in the output image. And the result is, for Gaussian, it only related to the distance at from the center. So it is, I should say here, okay, you cannot see any directions. But however, for the box filter, you can still see the edge of the horizontal and the vertical boundaries. Therefore, you can see some vertical and horizontal artifacts in the output image. So, is Gaussian filter a separable filter? Yes, it is a separable filter. How to say? Okay, so this is a mathematical expression of the Gaussian filter. And if you separate the x and the y, because this is an exponential term, so it can be separated as x squared, and this is the y squared. Okay, and here, this you can separate this into this term and this term. So for this is the horizontal one, and this is the vertical one. So it is also a separable filter. Okay, so it means if you want to apply Gaussian filter to certain image, you can compute it very efficiently. Alright, so this is the, okay, let's consider a practical question. Because you have, suppose you have an image, of course, the image has this boundary. And how do you apply those filters on the boundary pixel? Because let's take a look here. Okay, yeah, okay. We can calculate this point, no problem, because we have the pixels here. But how to calculate this pixel? All right, okay. So there are several ways to deal with the problem. Okay, it means you just fill 0. So this is 0 padding. So this is the original image, and you pad the zeros here. Then do image filter again. Of course, because these values are 0, you will generate a dark boundary. Then, okay. So compare with the original values here and here, the boundary, the pixel on the boundary is quite darker. And another one is called wrap. That means you just copy this region to its boundary. So you generate those pixels. Okay, let's take a break. Okay.
Yeah, I do want to go to the blog in a sense where while some are still active. But this weekend
Alright, so in addition to the radial pending, so the rapid pending means just copy the region. So from here you can see this region is copied to here, okay, and this region is copied to here. So it's just copy past the image to its surrounding pixels. And the claim means extend the pixel. So you can see they are extended pixels, okay. And this mirror means from one side to another side, like a mirror. Okay, so they will generate use different padding approaches. You will have different result, and so this is generated by the blur. So the boundary is slightly darker, and you will have blurred boundaries. Okay, for clamp and mirror. So the normalized zero is suggested by the author. Okay, so let me explain what it is. It means you still use the zero pending, but you will need to use another component called the alpha channel. And let me explain what is alpha channel. So this is alpha channel. It means if you have a image, it's called RGB, then you need one more channel. The channels mean the alpha channel, okay, or alpha matte. If you have, it means the transparency of those pixels. So this is example. It means if you have an input image and you have extracted, you remove the background, and you can, if you can decide the alpha channel, then you can combine the region with. You can replace its background by this equation. The generated image will be 1 minus the alpha channel multiply the background plus the alpha channel of the foreground. So alpha channel, or the value of alpha means how much the pixels will come from the foreground image, right? And let's go back to our here. It means if you have a zero padded image and you set alpha channel to this one, so the bright means it comes from, it's the pixel of the original image, and the zero means it is padded out. Then you apply the image filter on both of them, so you will generate the blurred zero image and a blurred filter, a blurred alpha channel. Then you divide the two images pixel by pixel. Then you will generate the normalized zero. So the advantage of this method is you won't introduce any new or extra pixel values. You just use the original one. Okay, and you can keep the boundary images the same as the input one. So this is the advantage of this method. All right, so they are linear filter, and some filters are nonlinear. So this is an example called a median filter. It means filters, if we want to replace, okay, filter out this value of 90, then what I will do is sort all of the surrounding pixel from the smallest one to the largest one. Okay, so it will be 10 and 15 comes from it, 20 from here, 23, 26. Then I take the median value to replace the original value. Okay, so this is a median filter. And if we draw some images, it will look like this. If this is input image, and I apply a median filter, and I set the depth, then I will count the 5 pixels. Sorry, again. I will count the median filter of this 5 pixel. Okay, then what it will be? It will be value as this one, rather than this one. Okay, so this is a result of the median filter. However, if I apply a mean filter, then the result, mean filter is a linear filter, just like a box filter. Okay, but on the 1D dimension, then the pixel of this extremely high value, they will be influenced. So you will see the value slightly is here, and it will generate a okay. So around close to the A region, those values are averaged. So you will see the smooth result. So median filter, in certain way, it can remove certain type of noise called white and paper. Okay, so this is an example. Given this input image, if I apply the silt and the paper noise, okay, this might generate the noisy image. And if I applied median filter, this will be the restored image. And I generated the 3 images using this piece of MATLAB code. Okay. It is a a useful language or useful programming tool for image processing. Okay. And this photo, it has its name. Its name is Cameraman. And I apply the noise function, and I can specify what kind of noise I would like. In this case, I use silt and paper. So silt and paper means silt is white, paper is black. So I add a lot of white and black noise onto this image. And then I use median filter. Just use this function, then I can apply median filter. And this generates the result, and I show this result out. Of course, if you enlarge this image, you still can see some detail disappears. For example, this one, this is a camera, right? And in the filtered the image, some details disappear, right? And okay, because MATLAB is a useful tool, so here I want to quickly go through how, if you want, how to install MATLAB. Basically, our universities purchased the license, so every student can use it for free, right? So how to do it is, okay, this is the website of our software download web page. Okay, but the problem is it only has Chinese user interfaces. So for international students, they will try to follow this. So once you log in, you can see there are 2 buttons to download the MATLAB. It's for Mac OS or for the Windows system. Okay, and I click it, and here you can see this is a key. It's a very long number, and there will be a network link. It's a license file. So there are 2 versions available for the MATLAB. 2022B or 2023A. So every year there will be 2 updates for the MATLAB product. Okay, so you may have a question. Since I can use Python, and every package on Python is free, so why do I need to use MATLAB? Okay, there are 2 reasons. First, MATLAB is maintained by a commercial product, so it's very robust. When you use Python, you may feel, oh, error. So what happens? How do I solve the problem? Or one package is incompatible with another package. Okay, because Python is an open language, and there is an open community. Everyone is developing its own package. They are not synchronized. But however, MATLAB is a commercial software and very expensive. So there is a company called MathWorks. It maintains the products well. Okay, and the second one is usually MATLAB is easier to use. Just like this example, I can use only 3 statements to create the result. But if you want to implement this in Python, you may use more 10 set statements, etc. Because you have to import something and clear the matplotlib library, etc. Okay. Oh, then first you need to. There are several options here, and please select the I have a file installation key, and copy paste the key. The key is here. Okay, and then you need to also input your license file. Okay, then in the installation page, you only need to select MATLAB, the primary program, and the image processing toolbox. That's all enough for our course. Because if you, of course, you can install every toolboxes, but it will use this. It will use maybe 15 giga hard drive space. Okay, but if you only install the two, it takes, I remember, 2.3 giga. It's relatively small. Okay, and because our license only support students on the campus, so if you want to use it at home or somewhere else, you need to the VPN to log in our campus so that you can use it. All right, so let's take a look of the difference of median filter and Gaussian filter. So for median filter, okay, there is a parameter. It is how large neighboring window you want to calculate the median value. So suppose say 3 by 3 or 5 by 5 or 7 by 7. Okay. Of course, when you enlarge the region, you will generate more blurred results. Okay, it's the same for the Gaussian. If I also set a 5 by 5, oh sorry, this is a typo. This is 7 by 7. Okay. Then there's another important parameter is the standard deviation or sigma in the Gaussian blur. So let's take a look. This is a result. For different sigma, you will get a different result. The larger the sigma, the blur the output. Then, okay, if I use a very small sigma, then I will still see many noise, the purple and the white here. If I use a larger sigma, then the noise will be blurred with its surrounding pixel. So it's less significant here, but you still see the noise slightly. Okay, so that's the difference between the two filter. Which one is better? It depends on your application. All right. So, and here, because of this type of noise, this is a purple and white. It means there is a lot of extremely large or extremely small values as the noise input. So median filter usually works better than the Gaussian filter. So there's another non-linear filter called bilateral filter. Okay, this is a figure shown in our textbook. But however, one of the property of our textbook, it only shows very high level aspect. So I find another copy of slides from on the internet to explain the detail. So let me explain. You can see this is a Gaussian filter, right? Okay, Gaussian filter. This is you only care about the distance. The distance will decide the region, and then there is no direction. And however, if you have an edge on your image, edge means on the one side the values are small, and on the other side the values are large. Then okay, if you just apply, if you have another filter called range filter, a range filter means for a pixel is the pixel nearby pixel similar to itself or different. So in this case, if we have a pixel at the center, okay, the center means say here, okay. Oh, sorry, what's that? Okay, here, okay, at the darker side. Then the range filter means for another pixel here, how similarity are the two pixel values. So it will draw like this one. This is the center, and this means the high similarity. And for pixels on the other side, okay, it means it values around here. It means the low similarity, okay. And if they apply the Gaussian filter, it means the range filter. Okay, then it will generate a filter like this one. It means for the high similarity one, it will use the Gaussian filter's weight. For the less similar pixels, it will reduce the weight to 0. Okay. Then apply this filter to the input image. It means we only do weighted sum for regions similar to itself. So it means what? It means he only do the Gaussian filter for this region and totally ignore this region. Okay, so the primary goal of the bilateral filter is to preserve the edge. Okay. So the slides I found is here, this copy. It was, I think this is a tutorial course in SIGGRAPH 2007. Okay, so it is means also it is the lecture is given by Paris from NIT. So let me see. If we just use Gaussian filter for the smooth region, and this is Gaussian filter, and for the edge region, and for the texture region, then this is our result. Everything becomes blurred. Okay. So how to solve the problem? It is the bilateral filter. It means that for smooth region, or it will apply the original Gaussian filter. But for edge region, it will apply half of the Gaussian filter, like this one. And this one, it will be ignored. And for texture region, it will apply the Gaussian filter. However, depends on the similarity of the pixel and its surrounding pixels. Then the generated result will like this one. It preserves the edge. Okay. So there are two terms will be used in the bilateral filter. One is the domain filter. Okay, it is the space weight. So Gaussian is the example, because for Gaussian filter, the weight of the Gaussian only calculated by the space. It means the distance from the central point to its surrounding pixels. Another is called range weight. Range weight is like this one. Here, this is the range weight. It will be calculated based on the similarity of the pixel or the region to its surrounding pixels. Okay, apply the two types of weighted and then sum them up and normalized with a factor. It will become the bilateral filter. And here is an example of the one-dimensional case. So this is a strong edge here. Okay. It means when we have the edge, we will average pixels at least. And if we want to reconstruct, we will average the pixel for this. We will ignore the pixels. Even they are spatially close to each other, but the range filter will move them out. Okay. And here is the set. If we want to reconstruct this pixel, we will only use regions like this and ignore this part. But however, on the contrast, if we want to reconstruct this, filter this pixel, we will only use this region and ignore this part. Okay. So this is the figure illustration. Okay, so it looks like what? If we want to reconstruct P, because the Q and P are the value of P are highly different. So for the range weight will become 0, and the multiplication of the space weight and the range weight here region, it will be almost 0. So we will only use this part to do weighted average. And then when it is a 2D image, it will be this one. So this is the pictures you see on our textbook. Okay, the author of our textbook just use the region and copy paste to our textbook. And how to calculate the two types of weight? So both of them are Gaussian distribution, and there are two parameters: one for space and one for range. Okay, so again, this is for this example. This is the Gaussian distribution for space. So here, okay, they will be calculated by the distance. And for range, for this one, they will be similar, and for this one, because they are dissimilar, so the range weight will be very small. And the authors show an example. Okay, when we set a different range factor and different space parameters, we will generate a different result. And if the range filter is the sigma r, I mean the parameter for the range filter is infinity, it means what? It means for every pixel on the image, you treat them the same. So it is just a regular Gaussian filter. Okay, here the author mentioned, why do we need to use bilateral filter? Here show an example. Okay, suppose, okay, this is a problem of flash photography. It means, say we have a digital camera, and then there is a flashlight on the digital camera or your cell phone. So, okay, I should say, on your cell phone, the flashlight is very weak. Right? And if you have a conventional digital camera or the DSC camera, there is a flashlight. It's much stronger. You can take two different photos. Here is one. If you turn off the flashlight, you will get this image. The color looks good, but there is a lot of noise. If you turn on the flashlight, then you will get this part. Because the wavelength distribution of the flashlight is different from the sunlight or the regular illumination. So the color will become quite weird or not balanced. However, the contrast or the edge of the image is quite good because there are sufficient illumination. So how do we combine the two images to generate a good output image? So this is called flash photography. Okay. So here we use bilateral filter. Why? Because okay, see, let's see here. So this is the image A. A means this part. So this is A. And this is F. Okay. So here we use a bilateral filter. Okay, here. And they have a joint bilateral filter. This joint bilateral filter, so we have two domain, right? The space domain and the range domain. Okay, the joint bilateral filter means it use apply the noise data to the space domain, but apply the flash the camera to the range domain. Why? Because although the color is incorrect, but the intensity is good. So the information of the intensity from the flash the camera is still useful. So it will be used to measure the similarities between two pixels. So it will be used for the range filters. Okay. Therefore, okay, this is the flash the camera. We apply the bilateral filter here to extract the edge information. Okay, and because this is the flash camera, there may be many shadows on the image. If you want to take some objects, then because of the flashlight, there might be the shadow, and you need to they need to remove those shadows. So there's another path here. They need to remove the shadow, and then apply those generated images together. Then this is the generated image. So this is why we need to use bilateral. I should say. Let me speak again. For computer vision, we want to understand the image. However, our input is also image, and the image processing helps us to have a better input data. That's called the image. So in this case, it is this one. Okay. When we apply the bilateral filter, it is the imaging processing method to the input image. Then we can understand it well and generate the output image we like. Okay, so now we see the bilateral filter, and this paper it was published. It was published in 2006. It's called Guided Image Filtering. So, however, I need to mention this paper because let me see the history. In 1998, the bilateral filter was published in ICCV. Okay. And in 1996, okay, joint bilateral filter was published. So this is the joint bilateral filter. Okay, it was published in SIGGRAPH. Okay, and 2 years later, he published the method guided image filtering in ECCV. And who is the He? Okay, he is a very, very famous computer vision researcher today because in 2015 he published ResNet. He is the first author of ResNet, and ResNet. Okay, it is studied when I should say in 2015 the release of net data is the shock of the network. I should say. Neural network, because today we see deep learning. It means the layer of networks, right? And in the beginning, how many layers? Maybe 8, for example, AlexNet. And a few years later, it becomes 16. It is VGGNet. And then it maybe go to 20 plus or 30 plus. And in 2015, when published his ResNet, he pushes the layer of networks to 128. So it is jump of the network and also the jump of performance. Okay. So today there are still many people using ResNet to achieve their task. It is still a very useful network architecture. So, okay, let's go back to 2006. So, okay, let me clarify why I say her rather than he. All right, Okay, because he is a Chinese, and his Chinese name is He Kaiming. However, in English, he because of in the Chinese H means and E means He, so He Kaiming becomes Kaiming He. So this is He rather than he, right? Okay. Okay, 好。Let's see what he want to. What he mentioned in this paper is, okay, bilateral filter is only a special case for the guided image filtering. So you can see bilateral filter and then become jointly bilateral filter and become a more general filter called guided image filter. And he want to show the difference of the two images. So let's see if you can see here. Okay, the BF means the bilateral filter. If you apply the bilateral filter to these original images, then there will be the artifact. But if we use their proposed guided image filter, then there will be no artifact like this one. And this is another case. And here is also again. So if this is the original input HDR image, when they use the bilateral filter, you will generate this result. But for layers, not. And here again, there are some artifacts along the edge, and they have no. Okay, so what I want to show you here is, so this is a common progress for computer vision. You release the method, and a few years later, somebody use your method to develop another method, and then the newer one is better. Okay, and then a few years later, maybe somebody else will find, okay, oh, your method is just a special case of ours. Okay, this is generalized, and of course they need to show why our method is better than yours, so they can be accepted by the conference. All right. Okay. So now let's talk about the binary image morphology. Okay, it is a relatively easy concept, and let me show. So we have a input image, and we have a certain structure. Okay, the structure can be. Let me show you. Then we do the convolution. Okay, for the input image, and you can see, you can imagine the structure. It means a kernel. You have the concept of kernel already because of our linear. Let's take a look. Kernel. Okay, there are 5 different kernels. 1, 2, I should say 1, 2, 3, 4, 5. Okay, here kernel means it's a small patch. Okay, there are some values on the patch, and for the okay, binary set, you have a certain kernel, but here we call it a structure. Then we do convolution just like the linear filter. However, we need to apply a threshold holding operation. Okay, if the value is the C value is pixel value is greater than a certain threshold, then we will set it as 1, and otherwise it is 0. And in addition, because this is a binary image morphology, therefore the S and the F, both of them are binary images. So let's take a look. Suppose this is the image Z, and this is my structure S. So you can only see the value 1 because it is a binary, either 1 or 0. Okay. Then there are some widely used binary operations. Dilation. Dilation means we set the threshold as 1. So it means if your surrounding pixel, if there is any pixel in your nearby region and its value is 1, then your value will be 1. So it means for the Z, okay, it will enlarged, dilated. And erosion means, it means in your surrounding pixels, every pixel need to satisfy the shape of the structure. In this case, it means for every pixel here, you need to, the 5 by 5 surrounding pixels all of them have to be 1. Then your output value will be 1. Otherwise, it will be 0. So it means erosion. So from A to C, you can see the slope means thinner. Okay. And majority means half of your surrounding pixels need to be 1. Then your output will be 1. So it looks like the original one. Okay. And the opening is this one. Here it is difficult to see but I will show it in the next slide. And the closing means you do dilation first, then you do erosion later. Then because dilation, you will make the structure thicker, and then you will shrink it back. So what will happen? Okay, suppose this is a hole. Then the hole will be filled in the output image. So this is the erosion, closing. Okay. And then let's see the example of opening, because this figure in our test work, it's difficult to see the result of opening. Okay. Here is an example. Again, I use MATLAB to show the illustration. Okay, so I load this file, circuit black and white from the MATLAB built-in images. So this is circuit black and white. And I create a structure. The structure is a square patch. The size is 40 by 30. It is a rectangle size. And then I use opening. Then this is output result. What does it mean? It means in your input image, if the region is greater than 40 by 30 and all of them are 1, then it will, in only this case, it will be drawn on the output image. So the meaning of opening is it can remove small object. If you do not want a small object, you can use the opening operation. Okay, and again, closing. This, as we mentioned, closing will fill in these small holes. Okay, so if your hole is not small enough, it will not be filled. It will keep the same, right? Okay, and why? Okay, now you have the concept of the binary morphography. And why do we need this operation? Because there are some applications they need such a. For example, this one. Of course, you know this. It looks like a fingerprint, the shape of the fingerprint. And but however, no matter what devices you use to take the photo, there are some noise, and you can see there are a lot of noise here and here. So even within this side, okay, there are many small noise within this shape. And then if you use certain binary morphography operations, you can remove that. So you get a clear image, and you can use this image for your computer vision progress. For example, fingerprint recognition classification. So again, so this is the reason why we need image processing, because image processing can give us a better input for our computer vision task. Okay, and there is another binary operation mentioned in our textbook. It's called distance transform. So what is distance transform? It means given a pixel here, I want to know the distance to this. What is the distance from this pixel to its nearest dark pixel? So it looks like this one. Given the human silhouette, okay, we will generate. The brighter means it takes more steps from the pixel to its nearest dark pixel. And here, this figure 3.11 is the example given in our textbook. So from here, it takes more steps to its nearby region than this one. So the value here is greater than this one. And okay, the question is, even though we know this, even though we have this distance transform, what can it do? Okay, here show an example. Given this image, okay, I don't know what kind of the image it looks like. Maybe a lot of cells, etc. Okay, so however, if I want to count how many cells are on this image, how can we do? Okay, here show example. The algorithm calls distance transform watershed algorithm. Okay, so as you can see, it looks like a segmentation algorithm. Given an input image, you want to segment different cells from your image. So how do I do? Let's explain it. Okay, first you do some binary operation. The easiest one is set a threshold and only keep the brighter region. Okay, but however, you will have a lot of holes, right? If we take enlarge this one, because here you can see there are many dark spots on each cell, and then what you can do? Just use the closing operation. So once you pick up a proper structure, then you can remove those holes. So you will get this one, like this one, and then apply the distance transform. You will get this image, okay? And then use the watershed algorithm. Watershed algorithm means, see, since you have the distance, and you try to pick up the largest distance value. Okay, say, if I do it, I will pick this point, and this point, and this point, and this point. All of them are the beginning point, and then you label their surrounding pixels. Okay, then you will get this output result. So you can know where those cells are and how many cells are on the image. So the distance transform, their mathematical expressions look like that. So how do we calculate distance? The more straight intuitive metric is the Euclidean distance, right? The Euclidean distance means what? Suppose we have the value k and l, then it is k squared plus l squared and take the square root. But however, there is another distance called Manhattan distance, or it is L1 known distance. Why it is called Manhattan distance? Because Manhattan is a region in the New York City, and there are a lot of large buildings or skyscrapers there. So it is like a block and another block. All streets and roads are either vertical or horizontal. So if you want to from one point to another point, you cannot go straight through those buildings. You need to go either vertically or horizontally and vertically. So therefore, it's called Manhattan distance. And then there's another distance called a chessboard distance. It means you only care about the maxima horizontal or vertical values. Right? So you can see here, it is a maximum of either of them, right? Okay. And okay, here, what distance should we use? Or what metric should we use? Again, it depends on our application. Okay. On our textbook, you can see this figure at 3.23, and let me try to explain what it means. It means it's an efficient computational method for only the Manhattan distance. For other two distance, no way. Okay, I should say no way. There is no efficient method to calculate the distance. But for the Manhattan distance, there is. How to do it? Suppose because okay, I should say let me take for this pixel. Okay, what is the Manhattan distance? Do you think? Manhattan distance means the shortest step to is 0 to any value with the to any pixel with a value of 0. So for this one, it will take one step, two step to this pixel. So the value should be 2. Otherwise, if we go to here, if it 1 step, 2 step, 3 step. Okay, and okay, so for this pixel, the distance should be 2. And how to calculate it? Manhattan distance only care about the vertical step and the horizontal step. So, okay, there are two paths. For the first path, it calculates the left and the upper side value. So here is, okay, if the value is 0, of course, the value is still 0. So if the value is not 0 in the input image, then it will use this mathematical equation. It means take a look of its left or its up pixel. Because there is no upper pixel, so they only took the left pixel. And compare the value. If there is a value, then add it up by 1. So here, okay, it is 1. Because it is 0 plus 1, and it okay, so it is 1. So for example, for this, okay, here is 1 and here is 1. If when we need to calculate next pixel's distance value, then it will take the first, this is 1 and this is 1. So this is 1 plus 1 is 2, and this is 1 plus 1 is 2. So which is the minimum? Its minimum is still 2. So the pixel, the value of the pixel here will be 2. Okay, and this is the reason why the value here is. So you can see why there are 2 green pixels here. It means it will only calculate the upper one and the left one. Okay, so this is the first pass. It will go through all of the pixels using this rule. And in the second pass, it will go through every pixel, but from the right top bottom corner and go back to here. Then after the 2 pass, you will get the F and the B maps. Then you just need to compute the minimum value between the 2 maps and get the final distance d. So if we take a look here, okay, we will here it is 2 in the value of b, and the value is 3 in the map of f. Then take the minimum one. So this will be 2 here, right? Okay. So this is the explanation for the figure on our textbook. And all right, okay. All right, so now we are going to introduce the Fourier transform. So first, who is Fourier? Fourier. All right, okay. Let's take a break. Okay. All right, so I would like to introduce the Fourier transform. So Fourier is a French mathematician. Okay, so his idea is straight, simple, but very okay, special in his age. Okay, his idea is given any function and it can be rewritten as a weighted combination of many sine and or cosine function. And during his period, so there are many famous mathematicians in this Lagrange, Laplace, Poisson. They don't believe him. Okay. But however, today we know it is almost true. Okay, and let me show you what is. So what is sine? So sine function. Okay, let's see. If we have a unit circle, and this is the degree between this edge, then the sine means the distance here. Okay, so if we draw the relationship between the degree and its value, it will be like it is circular. I should say not circular. The periodical function, right? And the formal definition of this function would be there is a amplitude and there is a sine function with a frequency. Okay, the frequency would be f, and it would be omega 2 pi times f. Okay, this would be the angular frequency, and then there's also a phase. So there are 1, 2, 3 parameters for the sine function. So the amplitude is a very straightforward or intuitive parameter. If amplitude is small, then the range of the function is small. If we slightly enlarge it to 1 or 2, you can see the range of the amplitude become larger. Okay, and the higher the frequency, the more oscillations, the cycles. So if we set the frequency as 0.3, so you will see this shape. If we increase it to 1, then you will see more cycles here. If we increase to 2, then there will be more additional cycles. So it is a frequency. The higher, the more oscillations. And the phase is, it is only a shift on the horizontal line. So if the phase is 0, then it begins from 0. Okay. If the phase is 1, then you can see there is a shift from the left to right, and this is also a shift 2. Okay, so this is the MATLAB code to generate those figures. Like so, let me show you slightly. Okay, so this is the amplitude, this is the frequency, and I set the phi here. All right, so I can use this sine function to create a sequence of value from x to y, and then I just plot it, and that's all. That's MATLAB code. So it's very short and elegant. Okay, so let's take a look of this example. Say if this gt, it looks like this. Okay, it is a sine of the 2 pi ft plus 1/3 of sine 2 pi 3 the ft. Then okay, it can be combination of it is a combination of this sine function and then another sine function. Okay, and if we show its frequency domain, it will like this. In R, in F and 3F, they are response. For other regions, there's not. Okay, so Fourier's idea is, okay, given any function, for example, this is a square wave function. So how can it be a combination of many sine or cosine functions? Oh, however, sine and cosines, they are equivalent, and the only difference is their phase. If the phase is half of pi, then they will be the same function. So his idea is, okay, in the beginning, suppose we have a sine function like this, and we pass another sine function, it will look like this function. And but however, if we add more sine function here, then this function will be modified like this one. And if we add more sine functions, and the amplitude is really smaller, and the frequency slightly increase, we will get this one. And if we add more, it will look like this one. So for any function, okay, it can be a summation of many sine functions. So for the square wave function, the frequency domain, the response of frequency will be like this one. And when can we use the idea? For one-dimensional data, okay, it's like the music. Because the sound wave, it is a one-dimensional data. It can be decomposed into many different sine functions. And that is a spectrum of the frequency. Okay, so for low frequency to high frequency, and this is the decibels is their amplitude. Okay, and okay, let me talk about the Euler's formula. Okay, it means now I should say we are very, very used to the real domain. And however, there is another domain called a complex domain. Okay, and the complex domain, the real domain is just a part of the complex domain. And if we express it mathematically, it's the real x-axis or horizontal represents the real part, and the y vertical axis represents the imaginary part. Okay, it will look like one. So the Euler's formula looks like if the natural exponential to the order j theta, it will be cosine theta plus j sine theta, and the j is the imaginary root of -1, right? Okay. So what is Fourier transform? In fact, it is a function from the real domain to the complex domain, and its definition would look like this one. So the hx is a real function, and its multiplication to the exponential negative natural exponential to the order of negative j omega x, then we will get the complex result like this one. This is so when we separate the Euler's formula into the two forms, the cosine omega x and the negative j sine omega x. Okay, usually we will use the notation. It means the f is the Fourier transform. Truly transform a real function to its complex function, and there is a discrete form. And for our computer vision applications, we use the more discrete form than the continuous form. So it was like this: from x to 0 to n. N usually means, I should say, this is 1D, so it is the sequence. And we need to assume, and actually we need to assume, usually we assume because we only see the limited samples of this signal, so we assume those signals will repeat itself and in in the follow. Okay, so here the x will only start from 0 to negative 0.1. N means the number of sampling points, and it will be a summation of the value divided by the n itself. Okay. So okay, here is the example of the. Okay, let's go back here. So for this, it is a convolution. Can you? Okay, let me go back to the definition of convolution. Okay. Okay, so this is the convolution operation, and let's go back to the Fourier transform. Okay, so this is the convolution operation. Convolution, the h and the exponential terms. Okay. And let's show the example of the convolution. Okay, so here, if you let's see, there is a if f is a square function and g is also a square function, the convolution means I will calculate the overlapped region. Here is the yellow region. Okay, and the result of the integer value will be the convolution value. Okay, and let's show you another example. Here, the g is a rectangle function, and the f here is this. Like this looks like a negative to the order, negative exponential to the order of negative. However, okay, when we apply the convolution operations, I will generate a new value. It is a t. Okay, so here let's show the figure of table 3.1 of our on our textbook. Okay, so these are the kernels we used for our one-dimensional linear filter. Okay, if we use the discrete form of the Fourier transform, okay, what function we will get? It will like this one. Okay, and for different filters, we will get a different transformed function. And if we draw the figure, it will like this one. So what is the meaning of these functions? Okay, the meaning is, so for the y-axis, it means the frequency, and for the axis is the frequency. For the y frequency, it means the response. So it means for the box 3 filter, the low frequency signal will be preserved, and to a certain frequency, there is no response. The response is damaged to 0. Okay, and for the box 5, it will preserve the most low frequency signals. And for certain frequencies, for this and this, there's no response. And for so linear box and binomial, they have a similar property. Preserve low frequency signals and ignore high frequency signal. However, for the Sobel filter, okay, this is really interesting. So let me imagine a case. It means it will remove the low frequency signal, and for certain frequency, it will have very strong response, and it will remove the another range of high frequency. Okay, so let me think. Let me take a look. So if there is a age. Okay, let me take a look at the example here again. For the Sobel filter, okay, here you can see, as we can see, for some ages the response is very, very strong, but for some ages, for example, this one, there is some ages, and there is some ages. The response are relatively small. Why? The reason is, if you have a certain age, it looks, it will the one and then the negative one, they will reduce to each other. So that is the reason why for the Sobel filters, if your value say it is just 1, 0, 1 for this case, and then apply this Sobel filter, the result you get will be 0. Okay, so it means for certain also for certain values okay, it will be 0, and for another frequency, the value will also decrease to 0. And then for the corner filter, so let's take a corner filter again. The corner filter is at okay, let's see the corner filter. Yes. Okay, so given the age, the corner filter will only respond to those high frequency results. All right, and in this table, okay, from this figure, we can see it only responds to the high frequency signals and remove all low frequency signals. Okay, so this is now we are going to look at the 2D Fourier transform, and okay. So in the 2D Fourier transform, we need to take two factors into consideration. First, is the horizontal frequency, and another is the vertical frequency. So this equation is written in this form, okay, and the discrete form is look like. So let's take a look what it would be given the image, okay, like this one. So this is the result generated by MATLAB. Okay, so what does it mean? It means at the center, it means the low frequency signals. So in these images, where are the low frequency signals? In fact, there are many. On the wall, the frequency is quite low. On the floor, the frequency also quite low, right? So you can see there are a lot of low frequency signals in the images. And here you can see there is a large values along this side. Okay, what does this mean? Where can we see in this image? Okay, it is the pattern here. You can see there are many slope line here. Okay, it is the result of on the floor and taken by the so these slope lines will contribute to signals of this frequency. Okay. Okay, and here I also mentioned something here. Okay, when you look at I should say, here we call this is a fast Fourier transform of the image. Okay, and what is fast Fourier transform and then Fourier transform? The fast Fourier transform is just remember like this. Okay, this is an efficient method to calculate the result, right? And the fast Fourier transform is also working this way. It can significantly reduce the computational load of a Fourier transform. Otherwise, if we take the mathematical equation like this, okay, this is the two-dimensional Fourier transform. So how many multiplication and summation need to be taken here? It is the order of n squared. Okay, and the Fourier transform, okay, it will reduce the computational order to n times log 2n. Okay, so it can, when the n is large, the reduced computational will be significant. So, but however, I don't want to mention that here, right? Okay. I think that for Fourier transform, that's enough for us, right? Okay. And here, this is the Sophia filter. And when we apply the Sophia filter, we will generate this result. Okay. So this, when we apply, okay. But however, if we use Fourier transform, then given input image, we generate its signals in the frequency domain. It will be like this. And the Sophia filter, it also can be converted into the frequency domain. It will be like this. And there is a very useful property. It means if we do convolution on the spatial domain, it will be equivalent to the multiplication in the frequency domain. So we can simply apply multiplication on this image and this image pixel by pixel. Then this is the generated image. And we apply the inverse fast Fourier transform and get this result. So this result will be identical to this one. But however, we can significantly reduce the computational load. Alright, okay, so let's take a few look. So this is the input image. And it's transfer the Fourier, it's fast Fourier transform the result will be like this one. And this is a box filter, and this is also the transformed Fourier transform. If we multiply this image and this image pixel by pixel, we will get this image. And then when we apply the inverse fast Fourier transform, we will get this image in the spatial domain. Okay, so it will be the same result if we apply linear filter of this kernel to this image. Okay, and see, this is the notation for equation for the fast Fourier transform. So here, the H is the image in the complex domain. So, and we apply this and back. Okay. So let me mention it. It means because H omega is a complex function, and we apply the integer in the complex function, the result of our hx, usually it is also a complex function. But however, how do we draw or how do we show a complex function as an image if there are some imaginary number? Okay. So when we show the image, it means we remove the imagined part. We only show the real components. And okay, the questions. Now we heard of frequency, I should say, fast Fourier transform. It is a transform from the spatial domain to the frequency domain. And what can it be used for? Okay. So this is a very famous book. It is widely used. The first edition was published in 1977, and the latest edition is 2018. So it is a long life method. And in addition to this book, there is another version, means digital image processing using MATLAB. Okay, there are also 2 editions, and you can get this book from our CGU library, right? Okay, so I use a few figures from the book to show you what Fourier transform can work for us. Okay, so this is called Moore pattern. Okay, it means because when you print something out or for the paper book, you use different inks, right? The cyan, magenta, and the yellow ink, or some of them use the black ink. And then when you print it out, you will generate like patterns like this. And if you read the paper in a distance, or you want to send the patterns on the paper, but if you take it very close, or if you use a scanner to get images from this paper, you will see the pattern on it. Okay, like this one. So this is the Moore pattern. And how to remove the Moore pattern? Use Fourier transform. How to use it? Okay, it means if we convert this input image into the special frequency domain, we will get this image like this one. And you can see there are some point here. Okay, that is the energy of those Moore pattern. So we remove those values. We just set it as 0. Okay, then we convert this modified high frequency data in the frequency space back. We will get this image. Okay, so the Moore pattern was reduced. If we remove more energy more data in the frequency space and convert it back again, we will get this one. Okay, so and another application is like this. This is a photo called Earth's rise from the lunar orbiter. It was taken in 1966. Okay, when the rocket or where humans the first time can go to the space and see Earth rises rather than moon rise. Right? Okay, but however, you can see there are many significant patterns here. Okay, again, we can apply Fourier transform to remove the signals of the certain pattern. And then this is a real case. However, this is a synthesized case. It means, suppose we have a photo. There are significant pattern following a certain frequency. Then we convert into the frequency domain. You can see 2 spotlights here. And we manually remove or set the 2 pixels as 0 and convert it back. We will get a clear image. So, however, this is synthesized. And this is the real case. It means this is X-ray. Everyone, the chest X-ray, nobody. And we apply the Gaussian high pass filter on this array. We will generate this result. Okay. And what is a Gaussian high pass filter? It's very similar like this. Let me go back to here. And this, okay. This is very similar to the Gaussian high pass filter. So this is a box filter, right? It is a low pass filter. And this is the you can see this to say it's a peak because only value 2 is there. Then you subject the low frequency filter with this 1. You will get a high frequency filter. Okay. Okay, then we apply, we add the high frequency signal back to this image, and then we will generate this image. And we apply the histogram equalization, as we mentioned in our previous, I should say, 2 hours ago. Then we will generate this image. So for doctors, this image will be much more useful than its original X-ray image. Okay. In addition, so there is a image transform called discrete cosine transform. It is a special case of the Fourier transform. So this is the equation for the DCT transform. Okay, so but what is the meaning? Let me show you. If we apply the discrete cosine transform, so say this is the 8x8 image patch, and we apply the discrete cosine. Let me show. Fourier transform is a conversion from real domain to the complex domain. But discrete cosine transform, it is a conversion from real domain to real domain. So there is no imagined part for this transform. And given for example, this patch, then if we apply the DCT transform, we will get the F coefficient like this metric. Okay. And we can use the inverse DCT to convert this matrix back to its intensity domain. Okay. And it is equivalent to, for this coefficient, we multiply it with this basis. And for this, we applied it to this basis, and etc. We apply the coefficient to its basis and sum it up. So it will come back to the input patch. So what can we use? How can we use the discrete cosine transform? Okay, so the answer is it is used in JPEG. Okay. JPEG is an image compression method, and it is still widely used when you download some JPEG file from the internet, or when you use your cell phone or digital camera to take a picture. Usually, it is saved as a JPEG file. All right. So how the JPEG method compress the image? Okay, it means for every image, it crop the image into many 8x8 patches. And for every patches, it convert the patches into the F metric. And for the F metric, it will quantize the value. Okay, so there's the first factor. How do you choose the quantized value? So for example here, the 415, it become only 26. And one of the DCT, the property of DCT is you can see from this DCC basis, which is the high frequency basis and which is the low frequency basis. Of course, you can see this is the low frequency basis, right? And this is the two bases here is their frequency is higher than this one. And for the three bases, okay, their frequencies are higher than their previous one. So, and this is the basis with the highest frequency. Okay, so it means when you see the zigzag line, it means from low frequency to high frequency. And DCT, when we have the F matrix, most signals are low frequency one. So when we quantize the F frequency, usually we will see this is a large value in terms of the absolute value. Okay, and other element values are small values. Okay, so you see there are many small values. So JPEG means first I can choose a proper quantile value to only preserve the large signal and then remove the large low frequency signal and then remove the small high frequency signals. And there are also Huffman code to reduce the overall bit of the B matrix. Then, okay, when you save an image into a JPEG, there usually is a number from 0 to 100. And when the number is large, you will get a file with we will get a large file. And when the quality value is small, you will get a highly compressed but a very, very small number. It means it controls the quantization values. And this is the result. The image is copied from Wikipedia. So it means for this region, it used a very high quality value. It means the compression rate is relatively small. And for this region, it used a relatively high compression rate. It means in turn it quantizes the F matrix very, very significantly. And in addition, you see this is a colorful image. And the colorful image means there are 3 channels, RGB. Okay, but however, JPEG for the digital for the DCT transform, it only works for grayscale, right? Okay, because this is a transform from a matrix to another matrix, and there's only single channel. So how do they do for the colorful image? Yes?
There is like 3 layers of matrix.
Okay, this is a way. But they didn't use this way. Okay, yeah, of course, I should say, what is JPEG? What does JPEG stand for? JPEG, well, it is the full name is Joint Photography Expert Group. You can imagine it's just a company. Okay, so they try different methods. The first is like yours, just separate the 3 channels and convert, then use the DCT transform. However, because you can see the standard of the JPEG, in fact, they convert the RGB image into another color space called YCBCR. Okay, YCBCR is very similar to the I didn't show YCBCR. Okay, here. Okay, however, it's somehow like the let me show. Can I take this one? Color space. If I would say it's somehow like this. Y means luminous or the brightness, and CB and C are similar like A and B. However, but the CIE or AB is perceptually uniform, and the calculation of CIE AB is relatively complex. However, YCBCR is a linear transformation from the RGB values. So to compute it is very easy and straightforward. But the meaning is similar. Y is the brightness, and the CB and CR, there are 2 axes of the color spaces. And because our eyes are relatively insensitive to the color, we are very, very sensitive to brightness. Okay, so here the JPEG format, what it will do is to convert the RGB space into YCBCR space and crop every Y 8 by 8 pages and apply the DCT transform, okay, and quantize, and then do Huffman coding to generate a sequence of data. But however, for the CB and the CR domain, first it will subsample it. It means the subsample factor usually is 2, but if you set the quality values very, very small, it means you want to highly compress the image. It will use a subsampling factor as 4. So then they will use the DC. They will apply the DCT transform again. Okay, so it uses the property our humans are insensitive to color the change, so it can highly compress the image. Okay. So look like this one. For this region, because the compression rate is very, very high, so you can see basically this is a brown cat, but here looks like a green part because here, due to the high quantization value, the colors here go wrong. All right, okay. So as we mentioned, the subsampling. Then here I show a concept of interpolation. It means upsampling. Okay. So this is a figure from our textbook. Given an input image, they are different. So input image means what? We have I should say matrix of 3-dimensional. Okay. I should say we have 3 channels RGB, and for each channel we have a matrix to present the image. All right. And then if we want image with a high resolution, so the interpolation means we generate pixels from its neighboring pixels. And there are several different ways: the bilinear, bicubical, and window the size. And the basic concept of interpolation is like this one. Okay, in our textbook, it is formulated as this one. So here, the F is the input image. Okay, so it has its own indexes K and L, and we have upsampling rate. For this example, the upsampling rate is 3. It means for small images, we will generate larger images. Its height and width will become 3 times larger. Okay. So what is interpolation? Interpolation. So we only have the F. F is the input value. Okay, so we have the value of F here. And we want to decide if there is an index I here, it is between RK and RK times R times K plus 1. Then what the value should be. And there are 2. So basically, this is the equation to decide what the G value should be. And there are 2 perspectives to explain this equation. First is every F point has its own value, and they will contribute to the G value with certain weights. Okay, so the weight is decided by the H function. So you can see there are many curves here. So for this curve, it means the contribution for this FK1 to the G would be this is a negative value. And for this Fk, it will contribute to the Fg is here. And for this K plus 1, it will contribute to G2 is here. And the G's value will be the summation of the 3 points. So this is the first perspective. Another perspective is G has its own weight distribution. It's like this one, the red one. And the F will multiply by the attribution and get it back to G. So when we want to decide another location, for example, this green one, then the curve is the edge. They are the same. It just move one pixel to another pixel and sum it up with different F value and country effect. So this is the example show our textbook, and this concept of those is like that. The nearest neighbor means suppose I have two nearby neighbors at the brown and the green one. The nearest one is which is the close one. I just use its value. And the linear is, okay, I suppose there is a linear function, linear line, and it will interpolate value of the two. And the cubic, it means a polynomial function of the order of 3. Then, so I need 4 points so that I can decide the cubic function. So suppose there are the 1, 2, 3, 4. And once I have this function, I can decide the value, okay, here. Okay. So this is for one dimension. And for 2 dimension is the same. I will use the value most close to me, and for bilinear, there will be first linear function and the second linear function, and there is additional interpolation here. And for bicubic, okay, there are 16 points, and I will use a surface on the 3-dimensional space and decide my value. Okay, so the question is, why do we need the nearest neighbor? Okay, the nearest neighbor is the one, the most simplest one. Just borrow the pixels from nearby values, pixels. This is the case. Okay. See if this is the DCT basis, and this, okay, this DCT basis. I crop this DCT from a paper, and the paper, it is the image on my screen is automatically rendered by the PDF reader. So the actual size of a basis is only 8 by 8, very small. And when the PDF reader renders the images on my screen, what interpolation method does it use? Bilinear. Okay, so what is the result of bilinear? So you can see, if I use the nearest neighbor, I still can see the pattern here. Oh, sorry. There is a, okay, yeah. But if it is rendered by the bilinear filter, it is almost like a gradually changed, but it's not the true case. So for some cases, we still need the linear function. Okay. All right. So that's all of our course today. Okay. Do you have any question? No. Okay. Suggestion. Next week, I hope you can find your teammates to do your term project. Right. Okay. That's all of our course today. Thanks.